Now that we know about the different types of energy changes that occur during a chemical process, we can study reaction mechanisms in more detail to understand how a reaction happens. When we look at a chemical equation and we see the reactants and the products, all we are really getting is the beginning of the story and the end of the story. Kind of like, once upon a time, they lived happily ever after. Well, a reaction mechanism explains what happens in between the beginning of the story and the end of the story. So a reaction mechanism is the steps that occur during a chemical reaction. Take this reaction between carbon monoxide and nitrogen dioxide. We can see that nitrogen monoxide and carbon dioxide are produced, but what are the details of this reaction? What really happens? Well, look at what happens as the process progresses from reactants to products. Carbon monoxide changes to carbon dioxide, and oxygen is gained. And NO2 forms NO, and oxygen is lost. These are the details of the story. If we expand this equation to include the details, we can include the activated complex. If a molecule of CO and a molecule of NO2 collide in the correct orientation with the appropriate amount of energy, the activated complex will form for an instant before these bonds are broken and formed to create products. Carbon monoxide is a carbon atom triple bonded to an oxygen atom. When an oxygen atom in a molecule of NO2 strikes the carbon atom in a molecule of CO with enough energy, the activated complex will form. This is the activated complex for the reaction. The dashed lines represent chemical bonds, intramolecular forces, that are either going to break or form. Remember, CO is going to gain an oxygen, so the dashed line between carbon and oxygen represents a bond that is forming. The proper notation for the formation of a bond ends up looking like an X, but it is really two arrowheads touching at the points. NO2 will lose an oxygen to become NO, so the dashed line between nitrogen and oxygen represents a bond that will be broken. The notation for breaking a bond is a slash. Notice that the breaking and forming of these bonds results in the formation of the products, CO2 and NO. Let's sketch the energy level diagram for this reaction. First of all, keep in mind the facts of this reaction. The reactants have an initial energy of 10 kcals. This is a one-step reaction mechanism that requires 32 kcals of energy. We also know that the enthalpy for the reaction is negative 54 kcals. Remember, the negative sign tells us this reaction is exothermic. Let's start by drawing a horizontal line at 10 kcals for the reactants, CO and NO2. In order for products to form, the reactants need to increase in energy by 32 kcals. This is the activation energy for the reaction. This means the hill or hump of the energy diagram occurs at 42 kcals. The peak represents the activated complex. When a molecule of CO and NO2 collide appropriately with 42 kcals of energy, the activated complex will form. Remember, the activation energy is the energy of the activated complex, the highest hill on the energy level diagram, minus the energy of the reactants. How can we find the energy of the products? We have to use this equation for enthalpy. Delta H for the overall reaction is negative 54 kcals, and we know the energy of the reactants is 10 kcals. So we can solve for the energy of the products. Negative 54 kcals plus 10 kcals is negative 44 kcals. This should make sense because for any exothermic process, the reactants are higher in energy than the products. Draw a horizontal line at negative 44 kcals to represent the products of this reaction. Now, complete the diagram. Notice that the change in energy from the products and reactants represents the enthalpy of the reaction. Negative 44 kcals minus 10 kcals is negative 54 kcals. All right, let's answer some questions using the energy diagram. A delta H of negative 54 kcals means the reaction is exothermic. So when we write the balanced chemical equation, 54 kcals needs to be written as a product. What is the potential energy of the reactants? We can see right here that the potential energy of the reactants is positive 10 kcals. What is the potential energy of the products? The products are here in the energy level diagram. They have a potential energy of negative 44 kcals. Is this reaction exothermic or endothermic? As I just mentioned, a delta H of negative 54 kcals means the reaction is exothermic. Also, any energy diagram that looks like this one, where the reactants have a higher energy than the products, represents an exothermic process. Is there more energy stored in the reactants or products? Well, I just answered this. Looking at the energy level diagram, it is easy to see that the reactants have a higher potential energy. Remember, you can also think about it in terms of the law of conservation of energy. 54 kcals of energy must be added to the product side, just so the products have the same energy as the reactants. So the reactants must have a higher potential energy. What is the value for the heat of reaction? This is delta H. Delta H was given in the problem, and we can see here in the diagram that it is negative 54 kcals. This is the question where you must include the sign along with the value. When in doubt, include the sign with the number. Where is the energy coming from? Intramolecular or intermolecular forces? A covalent bond between carbon and oxygen forms, while a covalent bond between nitrogen and oxygen breaks. Covalent bonds are intramolecular forces. What is the value of the activation energy forward for this reaction? Looking at the diagram, we can see that the activation energy for the forward reaction is 32 kcals. 42 kcals minus 10 kcals. How many steps or hills are in the postulated mechanism? There's only one hill, so this mechanism has only one step. What is the activated complex? The activated complex is the CONO2 intermediate represented in the brackets. By definition, the activated complex is the intermediate at the highest peak on the diagram. What is happening at the activated complex? As we discussed at the beginning, a bond is formed between carbon and oxygen, and a bond between nitrogen and oxygen is broken.